Okay, let's calculate out. What are we looking for? How much energy that this has, and I want to know what its frequency is. So rehashing this, frequency, units of frequency. Per second. Per second. All we're looking for is per second. The per part, the event, is wavelengths or waves per second. So I need seconds, and the way I'm going to get seconds is I'm going to go ahead and start with 3 times 10 to the 8th meters per second, and then I need to just get rid of the meters. So 5.5 times 10 to the negative 5th meters, and then my meter units cancel out. I get 1 over seconds, and so I have a frequency. And what is it?
5.45 times 10 to the 14th.
That sounds good. No, I'm pretty sure it's 14.
My calculator is spitting out 12, so I don't know what's going on, but it's probably.
Are you using E or are you using times 10?
I'm doing 10 carry.
Try punching in 3E8 divided by 5.5E negative 5. Three E8 divided by 5.5 E negative 5. No, it is 12.
Is it?
You made a mistake, Andrea. Oh, that's right, because this is infrared, not visible light. How much energy does it have? So the amount of energy that we need, or the units for the energy, is going to be joules. So to get a joule as our unit, we're going to use 6.626 times 10 to the negative 34th joules times seconds. And I need to get rid of the seconds, so I'll put 3 times 10 to the 8th meters per second, and then the seconds cancel. And then I'll put my 5.5 times 10 to the negative 5th meters down here, and the meter cancels out. So then I'm only left with joules. And so I've got a 6.626E negative 34. And looks like 3.6 times 10 to the negative 21st joules. We good with that?
Couldn't you also just take the 6.626 and whatever, and then divide it by, no, it'd be multiplied times the,
Frequency?
yeah.
Okay. Problem. Does anybody have a problem with that? Using the answer I just calculated to calculate my next answer? What if what you did was wrong? Which it was.
It was.
And 2, this is my answer with correct sig figs. Right? If this wasn't my answer, it was 5.45.
Yeah.
What I'll tell you is on the NCLEX exam and on nursing exams, when you're going to do a mathematical calculation, they'll trick you into doing this. And then one of the answers will be like a tenth different. But A will be the answer you got, and B will be the answer if you used the given information to calculate. So can I get this answer down here without using a given piece of information or without using a piece of information that I calculated? Yeah, I can use this along with the speed of light and Planck's constant, and I can get my answer. Then do it that way. Does that make sense?
Okay, yeah.
You will always have more error because there's going to be some calculation, rounding issues, and all kinds of different things. So if I can just get the answer straight with what I was given, then just go ahead and do that. Because I guarantee you that there are multiple choice, because it's a multiple choice test, right? There's only so much tomfoolery that you can do with a multiple choice test. This is one of the things that they're going to do, right? They're going to screw with your head by giving you an answer that you think seems to be perfectly acceptable because that's the answer I got, but we wrote 5.45. That should have been what we actually got here with a bunch of other decimal places, and I guarantee there will be an answer that's more correct if you use the given information. So the thinking is a multiple choice test is easy, so they need to make it hard. That's the way that they were thinking about that. That's the way the SAT works. And the ACT. Green light, blue light, so prove it mathematically. So how are you gonna do that? Well, you should probably go find yourself some green light or some blue light and get a wavelength. So I gave you this. So you could have just got a random, I don't even care what numbers you use as long as they apply. So what do you want to say, green? 5,
I use
515? Blue, what do you want to go?
450.
450 and 550? Do those sound good? Okay. So I'll say that my blue light, what's my blue light's frequency? Or my wavelength? This is going to be 450 nanometers, and this will be 550 nanometers. Okay. So I'll calculate both of these out. I'll go 6.626 times 10 to the negative 34th joules times seconds. And then I'll go 3 times 10 to the 8th meters per second. And then I'll put 450 times 10 to the 9th meters. No, negative 9th. And then I'll do the exact same thing with 6.626 times 10 to the negative 34th joules times seconds, and 3 times 10 to the 8th meters per second, and 550 times 10 to the negative 9th meters. So the meters cancel, the seconds cancel.
In the Tice constant, when you say joules per second, is
Now, it's not joules per second, it's joules seconds.
joules?
Joules times seconds.
Yeah,
All right, so 6.626 E negative 34 times 3 E8 divided by 550 E negative 9. Oops, that's 500. 550. And then I'll do 450. So for this one here, I got 3.19 times 10 to the negative 19 joules. And for this one here, I got 4.41 times 10 to the negative 19th joules. There you go. I just proved that the blue light has more energy than the green light. Yeah.
With the joule seconds, what type of parameter is that? Like,
It's not a parameter. It's a constant. So when you build a constant, the units of the constant are whatever you use to make the constant. Do you remember in the gas law stuff?
yeah.
That 0.08206 liter atmospheres per mole Kelvin? Well, how did we get it? It's because I took a volume and I multiplied it by a mole. I divided it by a temperature and volume and atmospheres were the things I multiplied by, and moles and temperature were the things I divided by. And so when I did that, none of the units canceled out, so all of the units stay. So when they calculated out what Planck's constant would be, the units that were left over after the calculation were joules and seconds. But a joule, is that just a unit? Is it just a unit like meters is a unit? Is joules a base unit? Lordy no. Oh no. It's a measure of energy, right?
Okay.
Okay, so how do you measure the amount of energy something has? There's a joule. A joule is actually equal, well, when you're talking about something's energy, the amount of energy it has, some things apply to it, right? Its mass means something. right? A bigger thing will have more energy than a smaller thing if all other conditions are the same. And then this meters squared and seconds squared, this has to do with the distance that was traveled, and it has to do with the acceleration during the travel. We okay with that? So if something's accelerating faster, if something's moving farther, and if something's heavier, then it's gonna have more energy. And so the joule is actually all of these units put together, and seconds. So really, the unit for the Planck's constant should be what? Shouldn't be joules, it should be kilograms meters squared per second. But they didn't want to cancel that out. They wanted to give you units that you might know, like joules and seconds, instead of that crazy kilogram meter squared per second. Okay. Did I answer your question? I don't even remember what it was. A given photon has 500 nanometers of light. Calculate the frequency, calculate the energy, and identify where it falls in the spectrum. So we already know it's like aqua blue, right? Because we just calculated a 450 and a 550 as green and blue. Okay, so let's go with 500 nanometer light, and then I want to calculate its frequency. So I will put 3 times 10 to the 8th meters per second, and I want to get rid of the meters. So I'm going to write 500 times 10 to the negative 9th meters. Are you okay with me doing that conversion in my head? What did I just substitute? Nano means 10 to the negative 9th. So I just got rid of the nano part of the nanometer by throwing in what nano actually means, which is 10 to the negative 9th. So then meter cancels out meter, and I end up with, I don't know what that is. 3E8 divided by 500e negative 9, and I get 6 times 10 to the 14th 1 over seconds. Okay, so there's my frequency. And then my energy, I'm going to go 6.626 times 10 to the negative 34th joules times seconds. I'm going to get rid of the seconds by using 3 times 10 to the 8th meters per second. And then I'll use my 500 times 10 to the negative 9th meters to get rid of the meters. And times 6.626e negative 34. And so I get 3.98 times 10 to the negative 19th joules. Okay.
Wouldn't it just be 4 though, like 6 days?
It would just be 4, because I only
A
have.
quick question about the.
Of course.
Making it, what is it, 5 to the negative, 500 to the negative, okay?
Yeah.
When I was like, I know this is like day one, but when I moved the decimal 9 spots from the 500, I don't know why I thought it was 10 to the negative 7.
It would be 10 to the negative 7th, but it also would be 5 times 10 to the negative second, and I left the 500 there. I literally didn't. Is this number here or this number here, are they in scientific notation? No, because it's a number in a decimal place. But if I bump that over to 5, you're right, these 2 zeros would knock it, that negative 9 down to a negative 7.
And that's okay.
Totally, yeah. I just did it quickly. That was it. Using a diagram, explain atomic line spectra. I guess my diagram would look something like this. That an electron that's in a higher orbital will drop down to an area of lower energy, closer to the nucleus, and in doing so, it will give off light. That light might be visible. It might be in the infrared range. It might be in the X-ray range. It could be anywhere along the electromagnetic spectrum, but it gives off some light. So atomic line spectra is simply an atom with excited electrons who are in orbitals they're not supposed to be in. And they don't want to be there, so they fall back down to where they're supposed to be, which would be ground state. And as they fall, step by step, they release light. And the light could be anywhere along the electromagnetic spectrum.
And they're excited because you're putting energy in.
Somehow I'm putting energy in. This, yeah, we'll just leave it at that. Energy in some way. Could be chemical, could be heat, could be some other source of radiation. So what evidence leads us to believe that light's a particle and a wave? So how about the wave part? What do we got? Refraction and what?
Diffraction, the arcing.
Interference. The diffraction and the interference. Both of these things are proving that light is a wave. And then the particle?
It's the photon photoelectric.
The photoelectric effect. So this is the solar panel effect. I can take my solar powered calculator that needs very little energy, put it underneath one of those giant red beef heating lights that is going to give plenty of energy, but it can't. And why does it not work? Why does the, it doesn't add.
It's not compounding energy.
I can't add the lights together. Each individual wavelength that's coming in, if it was acting like a wave, the waves, when they hit each other, they just get bigger and they have more energy. But they're not doing that. They're coming in individualized as little packets of energy that we're calling photons. And the photons can't be summed to cause an electron to jump from one level to another.